Hello everybody. Today we're going to go through section 6.2 of our Math for Teachers book, Problem Solving Approach to Mathematics for Elementary School Teachers. And in this section we're going to talk about addition, subtraction, and estimation with rational numbers, in other words, fractions. So here we go. When students first encounter fraction addition, it's really important that you give them an opportunity to see how that works using a concrete model, because you may remember from school that when you add fractions, the denominators have to be the same, and you add the top numbers, and then the bottom number stays the same. And if you ask students to just memorize that rule without understanding why the bottom number stays the same, they'll always have trouble with that. So if you give them a chance to see how it works in a concrete model, they'll understand why the bottom number has to stay the same, and then they won't have to remember it or memorize it. It will make just sense to them. And that way, that's really learning. So that's understanding, and that's what we want. We don't want students to memorize rules. We want to develop their understanding. So let's look at this area model for addition. This is called the area model because each circle represents a whole, and then you can see that some of the area is shaded. Now in this first circle, this represents one whole, like I said, and then this one has been divided into 5 equal pieces. So 1, 2, 3, 4, 5 equal pieces, and therefore this circle represents the fraction 2/5. Okay, now suppose we want to add to that this fraction, and notice that this circle also has been divided into 5 pieces, and only one of the pieces is shaded. So this would represent an addition of 1/5. So we know from previous lessons that the bottom number represents the size of the pieces, or how many pieces it takes to make a whole. So it takes 5 pieces to make a whole. Here I have 2 pieces, and here I have one more piece. So I have 3 total pieces, and it still takes 5 to make a whole. So 2/5 plus 1/5 is 3/5. And so a student could look at this and clearly understand that, okay, I see why the bottom number has to stay the same, because it still takes 5 pieces to make a whole. And the top number just represents how many pieces we're working with. And another thing that a student can develop from seeing the concrete model is that, okay, 3/5 is a little larger than 1/2, because you can see that a little more than half the circle is taken up by the shaded area. So this is the concrete model for addition, and I really like this. There's also the number line model for addition. So here we have a number line that goes from 0 to 1, and it's been divided into 5 equal pieces, so each piece again represents a fifth. So if this is 0, then this is 1/5, 2/5, 3/5, 4/5. This would be 5/5, but it's been simplified to 1. So of course 5/5 is equal to 1. And now if we want to add 2/5 plus 1/5 like we did before, we'll just draw one arrow that starts at 0 and goes to 2/5. And we'll add on to that another arrow that starts here and goes 1/5 more. And then you can see that the total is 3/5. So 2/5 plus 1/5 again is 3/5, and that's the number line model. Now here is another concrete model for fraction addition, and this one is called the fraction bar model. So in this case, we've got bars that are divided up into equal pieces. And so here we have a bar that's been divided into 5 equal pieces, and these 5 pieces represent 1 unit. So in this case, it takes 5 pieces to make a whole, but 3 of the pieces are shaded. So this would represent 3/5. And then in this second unit, again, it takes 5 pieces to make a whole. So these pieces are also fifths, but we have 4 of them shaded. So this would represent 4/5. Now if we want to add 3/5 plus 4/5, we can see that that's going to give us a total of 7 pieces. But how many does it take to make a whole? It still takes 5 pieces to make a whole. So 3/5 plus 4/5 is 7/5. And again, we see our rule in action that to add fractions, we just add the top numbers together, but the bottom number stays the same. And again, why? Because the bottom number doesn't represent the number of pieces that we have. The bottom number represents how many pieces it takes to make a whole, so that does not change. Now, what's interesting in this case is that we ended up with more pieces than it takes to make a whole. So if this represents 1 unit, you can see that we have extra pieces that go beyond the 1 unit. So this is what's called an improper fraction. If a fraction is greater than 1, it's called an improper fraction. Now, that just means that there's more than 1 whole unit here. The word improper is kind of unfortunate because it implies that there's something wrong with this fraction or that we ought to do something to it, and that is really not the case at all. Improper fractions are perfectly fine. In fact, it's easier to do arithmetic, add, subtract, multiply, and divide, with improper fractions than it is with mixed numbers. But any improper fraction can also be written as a mixed number. So why do we have both? If it's easier to do arithmetic with improper fractions, then why don't we just stick with improper fractions all the time? Why do we even talk about mixed numbers? Well, it's easier to add, subtract, multiply, and divide with improper fractions, but it's easier to visualize an amount if you're talking about mixed numbers. So we're going to talk in a few minutes about how to convert between these two forms, but just always know that improper fractions are fine. It's just that if you need to actually measure something or visualize something, you might want to change into a mixed number form. So here's the rule that we've kind of already seen in action in the previous examples. The definition of addition of rational numbers with like denominators. If a over b and c over b are rational numbers, then we can add them together by just adding the tops and leaving the bottom number the same. So a over b plus c over b is equal to a plus c in the top over b in the bottom. So see that that does not change when we combine the two fractions into one. Now let's talk about adding rational numbers with different denominators. So think about this problem. Here we have 2/3 plus 1/4. So here is a circle that represents 2/3, and here's a circle that represents 1/4. So in the first circle it takes 3 pieces to make a whole, and we have 2 of them shaded. In the second circle it takes 4 pieces to make a whole, and we have 1 of them shaded. Now, we can't add 2 pieces plus 1 piece and get 3 of anything because the pieces are not the same size. I'm sure that you see the problem here. In the previous examples, it always took the same number of pieces to make a whole, so we could just add the pieces and say we have this many pieces and it still takes 5 to make a whole in our examples that we did. But here, if I add these pieces, they're not the same size. So suppose that I did think that I could add 2 plus 1 and get 3. Well, then what would I use for my bottom number? The bottom number is supposed to tell me how many pieces it takes to make a whole. But for these pieces it was one size, and for these pieces it was another size. So what would we put here? You see how if a student understands what the bottom number means, they naturally will stop here because they will know that they can't put either number here because neither number does the job they need it to do. That's why understanding is so much better than just memorization. But anyway, in order to get a sum, we need all the pieces to be the same size. So let's think about how we might do this. Well, one thing that we could do is divide these two circles into the same size pieces. So now let's think about how we might do this addition. 2/3 plus 1/4. Well, we've already agreed that we can't say 2 plus 1 is 3 because the bottom numbers are not the same. So what can we do? Well, one thing we could do is divide both of these circles into smaller pieces so that all the pieces are the same size. Now, of course, if I take this circle and divide it into smaller pieces, I'm going to have more than 2 pieces. And the same thing here. If I divide this circle into more pieces, my 1/4 is going to become more pieces, but it's also going to take more pieces to make a whole, so the pieces will be smaller. All right, now let's think about what size of pieces might work here. You might say, well, I could divide each of these pieces into 2, and then we would have sixths. So it would take 6 pieces to make a whole. But can you do that over here? Can you take this circle and divide it into 6 pieces? Well, not if it's already been divided into fourths, right? So you look at this circle and you say, okay, well, if I divide each of these into 2 pieces, then they would be eighths. But then the question becomes, can you make eighths out of this first circle? And the answer is no, not if you've already got thirds. So you start to think, what's a number that 3 goes into and 4 also goes into? Well, that number is 12. So let's try dividing both of these circles into 12 equal pieces. Now this first circle, since it's already divided into thirds, that means each of these thirds is going to get cut into 4 smaller pieces. So I'm going to go ahead and do that. And now you can see that what used to be 2/3 has now become 1, 2, 3, 4, 5, 6, 7, 8 twelfths. And we'll do the same thing on this second circle. Now since this circle's already in fourths, each of these fourths is going to get cut into 3 pieces. So now it takes 12 pieces to make a whole, and 3 of them are shaded. So this 1/4 is equivalent to 3 twelfths. Okay, now the problem 2/3 plus 1/4 has been transformed into 8 twelfths plus 3 twelfths. So if we put those together on the same circle, you can see that 11 of the pieces are shaded, but it still takes 12 to make a whole. So these 8 pieces plus these 3 pieces gives us 11 total pieces, and it takes 12 to make a whole. And so finally we can say that 2/3 plus 1/4 is equal to 11 twelfths. I just want to emphasize to you one more time how important it is to allow students to have a chance to use concrete models to explore fraction addition with different denominators, because you really have to build that understanding of what's happening with the fraction addition before you teach them the algorithm. The tendency is to rush through because you're trying to cover fractions, and then you've got to cover other stuff, and there's a million things happening around you during the school day. And the tendency is just to say, okay, just memorize this and you'll be fine. But anytime you ask your students to memorize math steps, just know that they're not going to keep it much longer than past the test, because they're not going to have developed any understanding. They have to have a mental picture of what's happening before the rules and the steps will actually stick with them. So what happens is a lot of teachers teach the fraction algorithms too fast, too soon, and the students freeze up and they have trouble with fraction addition because the concept is too abstract for them. Remember, they're just little kids, and they can't visualize everything that you can visualize as an adult. It's actually a physical function of your brain to be able to think abstractly and to visualize things that aren't really there. And children often are not ready to do that yet, and we ask them to do that with fraction addition, and they feel confused, and they immediately feel like they can't do it, they're a failure. They don't like it, and then they shut down. This is the source of a lot of people's problems with math. So the answer to this problem is to spend time on it, be patient with them, practice, give them a chance to practice and use models, and never act like a child can't get it. Never put pressure on them or make them feel like a failure because they can't do fractions yet. They will eventually be able to do fractions unless you give them the idea that everybody can do it but you, or you can't do this and I explained it so many times so there must be something wrong with you, or you let their parents tell them that it's hard. Well, I never could understand fractions, and so I'm not surprised that he can't understand fractions. Don't ever do that to your students, and don't let their parents do that to them. You've never seen a grown-up that couldn't tie their shoelaces. Everybody ends up being able to tie their shoelaces, but it takes time. Not everybody learns to tie their shoelaces at the same time. So adding fractions is not a lot different. Everybody can learn to do it, but they have to be given a chance to grow into it. And you just never want to give them the idea that this is hard or this is difficult or it's no fun. And you have to keep going back to it and reviewing it. And you have to give them a chance to see and work with the concrete models so that they can really get a good grasp in their mind of what's going on. But the one thing I want to make sure you understand here is that memorization of the rules is not the answer. Do not teach your students some formula for adding fractions and think that you've done them a favor by making it easy for them to get answers. Working problems is not really the goal in math. We often feel like working problems is the goal, but working problems is not the goal, but understanding the concepts is the goal. So memorizing doesn't lead to understanding, so memorizing is not the solution to this problem. Okay, here is an example for us. We're just going to find each of these sums, and we're going to use the ideas that we saw with the concrete models, but I'm going to lead you toward a little bit more of an abstract algorithm for finding these answers. Okay, here we have 2/15 plus 4/21. And we know that in order to add fractions, all the pieces have to be the same size. In other words, the denominators have to be the same. So what we're looking for here to make these denominators the same is a common multiple, and we would like for the number to be as small as possible, so we're looking for the least common multiple. Now think back to section 4.3, where we learned how to find least common multiples. And so I'll work through that with you. The first thing we're going to need to do is find the least common multiple of 15 and 21. So let's list the factors. The factors of 15 are 3 and 5. The factors of 21 are 3 and 7. And so when I make my least common multiple, the least common multiple for 15 and 21 needs to contain a factor of 3, and it needs to contain a factor of 5, and it also needs to contain a factor of 7. Now notice that 15 would go into this number. We haven't found this number yet, but we've built it. So notice right now that 15 goes into this number because it contains factors of 3 and 5. Notice that 21 would also go into this number because it contains factors of 3 and 7. So basically this number is 15 times 7, but it's also 21 times 5. You see that? So 3 times 5 times 7, if you work it out, turns out to be 105. So 105 is our common denominator. So now I need to turn 2/15 into something over 105. You probably noticed when we did the last example where we had to cut the circle into 12ths that if we change the number of pieces it takes to make a whole, we also must by necessity then change the number of pieces that we have, because if the pieces get smaller we have more pieces. Okay, so if I take 2/15 and I can see here that 105 is 15 times 7. So if I have 2/15, I'm going to need to multiply this by 7 over 7 to get my new fraction. Now likewise, if I want to turn 4 over 21 into a fraction that has 105 as its denominator, then I'm going to need to multiply 21 by 5, because look right here. 3 times 7 makes 21, but I also need a factor of 5. So I'll multiply this fraction by 5 over 5. Now, you are going to want your students to understand why you're able to do this. Why can I do 2/15 times 7 over 7? And why can I do 4/21 times 5 over 5? Well, any number over itself is 1. So all we're really doing here is multiplying this fraction by 1. And all we're really doing here is multiplying this fraction by 1. And multiplying by 1 doesn't change the value of it. But notice that my 2/15 is going to become 14 over 105. So now it takes 105 pieces to make a whole. I've multiplied the number of pieces it takes to make a whole by 7, but I've also multiplied my number of pieces that I have by 7. I used to have 2 pieces. Now 2 times 7 is 14, so I have 14 smaller pieces. And the same thing happens here. 21 times 5 is 105, but my 4 pieces also gets multiplied by 5, so now I have 20 out of 105. And then 14 plus 20 is 34, so I have 34 over 105 as my final answer. Now let's look at part B. So this problem is actually written a little strangely. We have 2 over negative 3 plus 1 over 5. And so your students are going to say, well, how do you have negative 3 pieces to make a whole? Well, the answer is, of course, it's possible to divide by a negative number, but we don't usually write negative numbers in the denominator of a fraction. So you've already learned that a positive divided by a negative gives a negative number. So it's customary to write this negative either out front or in the numerator of the fraction. We usually try not to leave a negative in the denominator. So the first thing I'm going to do is restate this problem so that the negative is actually in the top. That's where I like it. Okay, now we can deal with both of these fractions. If my fractions have denominators of 3 and 5, then of course the denominators are different sizes and we're going to need to make them the same. So we need to look for the least common multiple. Well, the smallest number that 3 and 5 can both go into is 15. So that needs to be our common denominator. 3 times 5 is 15. So I'm going to be changing both of these fractions so that they have denominators of 15. We'll take our negative 2 over 3 and we'll multiply that by 5 over 5. Now you're going to say, how did you get the 5? Well, I know that I want the new denominator to be 15, so whatever it takes, 3 times whatever it takes to make 15 is what I need to multiply by. But I have to multiply the same thing in the top and the bottom because I'm really just multiplying by 1. And then the same thing here, I have 1/5, but I want the new denominator to be 15. So what does it take to multiply times 5 so that you get 15? Of course you need 3. So I'm going to multiply this fraction by 3 over 3. Alright, now multiplying these two fractions together, negative 2 times 5 is negative 10. So this fraction becomes negative 10/15. And for this pair, multiplying 1/5 times 3 over 3 is going to give us 3 over 15. Now we can add the tops, keep the denominator the same. So negative 10 plus 3 is negative 7, and the denominator is 15. Now one thing a lot of students have trouble with, I'll just go ahead and throw out here for you. A lot of students will say, after they do this step where they've multiplied the same thing in the top and the bottom and they've got this fraction, they'll say, oh look, both of these fractions can be simplified, and they'll simplify the fractions and then they'll try to add these two fractions together. Now I know you're saying, well look, if they do that, then they've just gone right back to the original problem. They've undone everything they just did. I know that and you know that, but a lot of students won't see that because they're just thinking about the steps they know how to do. They're not thinking about what needs to be done. So you might point out to your students sometimes that yes, these fractions can be simplified. Of course they can be simplified because we just unsimplified them on purpose. This was a simplified fraction when we found it, but we unsimplified it on purpose so that we could have like denominators. Of course these fractions can both be simplified because we just got done unsimplifying them. So be on the lookout for students that want to simplify their fractions just because they know how to simplify fractions. The point here is that we need fractions that are not simplified because we're willing to give that up in order to get the denominators the same. It's important to leave your answer as a simplified fraction, but when you're trying to add fractions, they won't always be simplified. Of course they can't be. And now let's talk about this negative sign a little bit. So we said earlier that we don't like to have a negative in the denominator, and here I have my negative written in the numerator, and that's fine, but I just want to remind you that it's also fine to write the negative sign out in front of the whole fraction, because a negative divided by a positive gives a negative quotient, or we could just put the negative in front of the whole quotient, so negative 7 divided by 15. Either way is fine. Okay, now we're going to work on a problem that has 3 fractions. So here we have 3/4 plus 1/5 in parentheses, and then we have plus 1/6. Now the parentheses here aren't really doing anything, so one approach might be to just go ahead and remove the parentheses and then find a common denominator for all 3 fractions. That is certainly an option, but it's not necessary, and it does overwhelm students sometimes when they're first learning to add fractions to think about finding a common multiple for 3 numbers. So there's no harm in finding the least common multiple for these 2, and then after you've added these 2, find the least common multiple for that one and this other 1/6 that we have here. So let's approach it that way. Let's first just worry about finding a sum for 3/4 plus 1/5. So we'll need to think about a least common multiple for 4 and 5, and of course that number is 20. The smallest number that 4 and 5 can both go into is 20. Okay, so now we're adding these 2 fractions, And we know we need to convert both of these so that they both have a denominator of 20. So I have to ask myself, what would I have to multiply by 4 to get the denominator that I want, which is 20? Well, of course, I'd have to multiply by 5, so that means top and bottom have to both be multiplied by 5. And when I do the 1/5, what would I have to multiply by 5 to get the denominator that I want? So I'd have to multiply 5 by 4 to get 20. So this 1/5 is going to get multiplied by 4 over 4. Okay, that gives us 15 over 20 for the first fraction, and it gives us 4 over 20 for the second fraction. Again, notice at this point we have unsimplified both of these fractions on purpose so that we can add them. So there's no use trying to say, should I simplify these fractions, because we've just unsimplified them. And now we need to add. 15 plus 4 is 19, so we have 19 over 20. And now this 19 over 20 needs to get added to 1/6, because remember we were supposed to do this sum plus 1/6. So we have our original problem, which has now become 19/20ths plus 1/6, and we'll need to find a least common multiple for 20 and 6. Okay, so the bigger the numbers get, the harder it is to think of the least common multiple. Notice that here 20 and 6 share a common factor. So 20 times 6 would give you a common multiple, but it's not the least common multiple. It's not the smallest number we can work with. So one thing you could do is do the fraction tree thing and use the algorithm for finding the least common multiple like we did back in section 4.3, but that gets a little tedious sometimes. So another thing that you will want your students to be able to do is find the least common multiple by thinking through the times table. So what I'm going to do here is just take the larger of the two numbers, which is 20, and run through its times table until I find something that 6 can go into. Well, 20 times 1 is 20. Of course, 6 can't go into 20. 20 times 2 is 40. 6 can't go into 40. 20 times 3 is 60. And aha, 6 can go into 60. So my least common multiple is 60. See how that works? Just run through the times table for the larger number until you find something that both numbers can go into. Okay, so we know now that we need to convert both of these fractions so that they have denominators of 60. So in order to change this 20 to a 60, I'll have to multiply by 3. And in order to change this 6 to a 60, I'll have to multiply by 10. So this fraction gets multiplied by 3 over 3. This one gets multiplied by 10 over 10, because remember, if you change the number of pieces it takes to make a whole, you also are going to have to change your number of pieces that you have. So 19/20 times 3 over 3 gives us 57 over 60. 1/6 times 10 over 10 gives us 10 over 60. And then 57 plus 10 is 67 over 60. And now this fraction cannot be simplified, but it could be converted to a mixed number if we wanted to do that. However, we're not required to do that because this is not a mixed number problem. So I'm just going to leave this answer in improper form, and that's perfectly fine. Now let's get a little more abstract. Here in example 6, we have some fractions that have variables as their denominators. But we're going to be using the same process to add them. So don't be alarmed. You know, a lot of students freeze up when they see variables. But if you understand the concepts that are used to work the problem, then there's no need to freeze up just because there are variables introduced. Variables are not letters. I've heard a lot of people say, I was doing just fine with math until they started putting letters in there, and then everything went to pot. Math shouldn't have letters in it. Well, you know, I've got good news for you, because math does not have letters in it. Math has variables, and we use letters as symbols to stand for the variables, but guess what? These are numbers. These are numbers that are represented by letters because we don't know what the number is. This could be 3 over 5 or 3 over 7 or 3 over 10. We don't know. So we're just going to put a symbol in place of that unknown number. And the same thing here. So these variables will have to behave the same way numbers would behave. Well, since x is one number and y is apparently a different number, then we can assume that these two fractions don't have the same denominator. So before we add these fractions, we'll need them to have the same denominator, so we'll have to get a common multiple. So the least common multiple here needs to be x times y. So whatever this number x times y is, it's clear that x can go into it because it has a factor of x, and y can also go into it because it has a factor of y. So this will be our least common multiple. Now, I'll be writing fractions that have the denominator xy. So if I start with a fraction of 3 over x, what will I have to multiply by to get this denominator that I want? Well, right now the denominator is an x, and I want it to be xy, so I'll need to multiply by y over y. And the same thing here. This fraction is 4 over y. If I want the denominator to be xy, then this fraction already has a y in its denominator. Now it needs an x. So I'll multiply by x over x. And again, it's easy to remember that you have to do the same thing in the top and the bottom because all we're really doing here is multiplying by 1. So whatever you do to the bottom, you must also do to the top so that you're multiplying by 1 and not changing the value of the fraction. All right, now we'll go ahead and do this multiplication here. So this gives us 3y over xy. And this gives us 4x over xy. And again, somebody's always going to say, well, look, you could cancel out the y's. And you can say, yes, but if you cancel out the y's, you'll just go back to this up here. And you'll undo what we just did. So you don't want to undo the step that we just got done with. All right, now notice that the denominators are the same. And so all we need to do is add the tops, but these are not like terms. So all we can do is just write them together, but we can't really add them like 3 plus 5 is 8. We can't turn it into one term, but we can just show that they're being added together. So in our answer, we'll have 3y plus 4x for the top, and of course the bottom is xy, because when we add fractions, the bottom number stays the same. Okay, now in party, we have a very similar thing. So first we're going to need to find a least common multiple. Well, we can see that we're going to need an a squared in our least common multiple, and we're also going to need a b. And now when we come to the second denominator, well, we already have an a, so we already have a squared, so we don't need another a there. We already have enough of that. But this is saying that we need at least b squared, and we don't have b squared, we just have b, so let's just make it squared. Okay, now let's just make sure that this is the right least common multiple. So we want to make sure that each denominator shows up over here. In other words, we want to make sure that this least common multiple has enough factors to make this and also to make this, though not necessarily at the same time. So for this first denominator, I need to make sure that my common denominator contains at least 2 a's and a b. 2 a's and a b, and it does. Okay, now I also need to make sure that it contains at least 1 a and 2 b's. 1 a, 2 b's. So we do have at least enough parts to make each individual denominator, and that's what makes it our common denominator. Okay, so now let's figure out what to multiply by to get this denominator. This denominator already has 2 a's and a b. Apparently, to get this denominator, all we need is an extra b, so let's multiply that by b over b. And this second fraction has an a and 2 b's. To make this denominator, we just need an extra a, so we'll multiply that by a over a. Okay, now putting these together, this is going to become 2b over a squared b squared, and this one is going to become 3a over a squared b squared. And now you can see that the denominators are the same, so when we add the tops, they're not like terms, so they won't combine. But we'll have 2b plus 3a in the top, and in the bottom, a squared plus b squared.